Assalamualaikum warahmatullahi wabarakatuh and good morning. My name is Nur Syakiri binti Niza and I am from 2BEKG S1. And this is my group members Gohan Singh, Nur Najwa binti Muhammad Azri and Kau Putsa. The title of this video is Class B Power Amplifier and I'm going to present about the popular types of push-pull Class B amplifier, the advantages of Class B versus Class A power amplifier and the disadvantage. Now, we look about the most popular type of push-pull Class B amplifier by using two transistors NPN and PNP and both positive and negative power supplies. A single input signal is applied to the base of both transistors. The NPN transistor provides the positive half cycle of the AC signal across the load, and the other PNP transistor provides the negative half cycle of the AC signal across the load. We look at the advantage of Class B versus Class A power amplifier. First, the use of two transistors make the Class B power amplifier provides greater efficiency compared to one transistor. Also, more power can be transmitted to load and eventually increase the efficiency. And lastly, the transistor dissipated only small amount of power. This disadvantage need two separate DC voltage supplies and produce crossover distortion in the output signal. That's all from me. Now I will pass to my friend to continue the slides. That's all from me. Thank you.
Hello to our lecturer Puan Wahida binti Abdul Halim. My name is Gohan Singh from U10 BEKGS1. Today I am going to explain our design circuit Class B power amplifier. So in this circuit diagram, we connect with VCC in positive 10 volt and below here we connect with negative 10 volt. And we also have AC supply. We set it to 10 voltage and we use two transistors in this circuit design. One is NPN and below here is PNP, BJT. And lastly, we connect to one resistor load in 10 ohm. So after run our simulation, we have get a value in PNP and NPN. First, we focus on transistor NPN. We get the IC value, which is current collector in 13.01 picoampere. And IE, collector emitter, we get negative 11.37 picoampere. And IB, base current, we get negative 1.644 picoampere. VBE, we get 10 volt. On the other hand, in transistor PNP, we get the simulation result IC current collector, we get negative 13.67 picoampere. IE, current emitter, we get 10.87 picoampere. And IB, base current, we get 2.807 picoampere and VBE is negative 10 volt. So here, when NPN transistor on, PNP transistor off, we get the positive cycle waveform. So the positive cycle waveform, this can see that IC in X75.722 milliampere, which is the maximum peak value. And when NPN on, PNP off, we perform a negative cycle in the simulation. We get the negative cycle minimum peak ampere IC is negative 890.3 milliampere. In this slide, the table below shows the value of DC analysis calculation and simulation. For NPN BJT, positive cycle will perform in our waveform, which is when the BJT NPN on, BJT PNP off. We set to the NPN BJT beta value is 100, and VB voltage base is 0, and IB is 0 ampere because we have no resistor in our circuit. To find IC, we use the formula beta multiplied with IB, which is 100 multiplied with 0, we get the IC value is 0 ampere. To find IE, we use the formula beta plus 1 IB. 100 plus 1 multiplied with 0, we get the value is 0 ampere in IE. Actually, VCE is equal to positive VCC, so we can directly get it in 10 volt. For PNP BJT, the waveform perform in negative cycle. So the value ICQ value becomes smaller closer to 0 because during this time BJT NPN is off, BJT PNP is on. We also set the beta value in BJT is 100, VB is 0, and IB base current is 0 ampere because also same we have no resistor in our circuit. To find IC, we use the formula beta multiplied with IB, 100 multiplied with 0, so we get the value is 0 ampere. To find IE, we use the formula beta plus 1 IB, which is 100 plus 1 multiplied with 0, so we get the value is 0 ampere in IE. Actually, to find VCE, we can directly get it equal to negative VCC, which is negative 10 volt. So the above is my presentation part. Now I pass the next part to my group member, which is Nur Najwa, to continue their presentation. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Najwa binti Muhammad Azri. So today I would like to present the calculation of power and efficiency. So firstly, it's already given current load peak 1 ampere and resistor load 10 ohm. So firstly, we have to calculate voltage load peak. Voltage load peak formula is current load peak multiplied by resistor load, and the answer is 10 voltage peak. And for IDC, formula for IDC is equal to 2 divided by pi multiplied by I load peak is equal to 0.637 ampere. And for input power DC, the formula is VCC multiplied by IDC, and the answer is 6.37 watt. And for output power AC, in AC, the formula is voltage load peak square divided by 2RL is it will equal to 5 watt. And for efficiency, the formula is output power divided by input power and multiply with 100 equal to 78.5%. And for maximum power dissipation, the formula is 0.5 multiply 2 VCC square divided by pi square multiply R load, and it equal to 1.103 watt. For power dissipation, the formula is input power minus output power divided by 2 equal, the answer is 0.685 watt. That's all from me.
Hello, my name is Kaopu, and today I'll be explaining the crossover distortion in amplifiers. Crossover distortion is a common feature of Class B amplifiers where the non-linearities of the two switching transistors do not vary linearly with the input signal. Crossover distortion produces a zero voltage flat spot on the output wave shape as it crosses over from one half of the waveform to the other. The reason for this is that the transition period when the transistors are switching over from one to the other does not stop or start exactly at a zero crossover point, thus causing a small delay between the first transistor turning off and the second transistor turning on. This delay results in both transistors being switched off at the same instant in time, producing an output wave shape. This here is an output waveform of our project circuit simulation, and as you can see here, there is a slight crossover distortion found in the waveform. Crossover distortion in audio power amplifiers produces unpleasant sounds. So, how can we reduce the crossover distortion? The crossover distortion can be reduced by using a slight forward bias in the base circuit, such as the transistors that are idling at a small output current. The forward bias causes the circuit to operate in a Class AB mode, so both transistors are slightly on during crossovers. In other words, we can use Class AB power amplifiers instead of Class B power amplifier to reduce the crossover distortion. And that'll be all from me and my team. Thank you.